Welcome to the Quarter 1 exam review. All right, so this first type of problem is trying to have us use the properties of numbers to justify steps in an algebra 1 problem. So the key to this is to look at what changes from each line to from the line above it. So in the first two lines, what changed? Well, right here, 3x plus 4x changed into 3 plus 4, the quantity 3 plus 4 times x. So those must be equal. And so if those are equal, what property does that represent? Now, a lot of times it's hard to see this, and so I'm going to flip it around a little bit, just a little bit, and we should have an easier time of seeing what's going on. Is that if we look at this, the x is being distributed. And so this is the distributive property that's being displayed there. So for the second step, it says simplify. So then, what's happening between here and here? Well, something was added to both sides of an equation. Whenever something is added to both sides, we have a property of equality. And so we have to ask ourselves, all right, was it the additive property of equality or the multiplicative property of equality? Did we add something to both sides, or did we multiply something to both sides? And it's very clear that we added. So that, actually, let's do this. So then, we have to look at the next step. What changed between this step and this step? Well, they added parentheses. So let's write what was on the line above, and then what was on the line below it. So those two. So what changed? Well, we added a set of parentheses. And whenever we add parentheses or move parentheses around, that's the associative property. Doesn't like my eye. There we go. So the associative property. All right, next up we have between this line and this line. And what changed? This turned into this. So what property allows me to say that if I add something plus its opposite is 0, and that's the inverse property of addition. Next up, this changed to that. So 6x plus 0 equals 6x. And if the property being displayed here is that if we add 0 to something, it doesn't change its identity. So this is the identity property of addition. Only a few steps left. It says simplify, which they do. And then they, once again, what changes between this line and this line? Well, they did something to both sides, and they multiplied by both sides. As we said earlier, if they multiply both sides, it's a property of equality. If they do anything to both sides, it's a property of equality. So in this case, they multiplied to both sides. So we have the multiplicative property of equality. Then, what changes now between this line and this line? Well, they took this and they turned it into that. So what makes 1/7 times 7 equal 1? So now we did change the identity. And if we multiply anything times its reciprocal, we get 1. Or anything times its inverse. And when we see that, that's an inverse property, and we multiplied, so that's going to be it's going to be A, the inverse property of multiplication. We're almost done now. So what changes between this line and, oops, sorry, already did that one. Between this line and this line? Well, we took 1x and we just turned it into x. So what allows me to say 1 times anything is itself? Well, that's an identity, obviously, and it's the multiplicative identity. And where's the identity property of multiplication? And so that is how we do the first problem. The key is to look at steps and say what changed between each step. All right, so now we have the problems where it says solve each equation inequality, then graph, show all work, express the solution using interval notation. So I'm actually going to make this a little bit bigger, give myself a little bit more room to work. So I need to get the absolute value part of the problem alone. So the trick I always show is think of this as if all of this was one thing, like say 2x minus 8 equals negative 4. Well, what would we do? Well, the first thing we'd do is we'd add 8 to both sides. Then we divide both sides by 2. And we're going to do the same thing here. We're going to start off by adding 8 to both sides of the equation. Now I have 2 times the absolute value of 2r plus 3 equals 4. Then I'm going to divide both sides by 2. 2's cancel. So now I have the absolute value of 2r plus 3 equals 2. You can see we did the same process we did over here in the green. So now, remember, if the absolute value of 2r plus 3 equals 2, that means that either 2r plus 3 equals 2, or 2r plus 3 equals negative 2, but when we took the absolute value, it came out 2. So we have to solve each one of these pieces individually. And I'll get 2r equals 5 divided by 2. And I like fractions, but I know you guys like decimals, so I'll write it that way. 5 halves are 2.5. Over here, I subtract 3 from both sides. Oh, I made a mistake. I'm sorry. Well, let's stop and start. Well, the mistake is right here. 2 minus 3 is not 5. 2 minus 3 is negative 1. So I'll get r equals 1/2 or 0.5. My apologies for the mistake. 2r equals, so now we're solving the other side. Subtract 3 from both sides, divide both sides by 2, and I'll get r equals negative 5/2 or negative 2.5. So we have to put those on the number line. Now there's no shading because this is not less than or greater than, it's just equal. So the interval is not really correct, it's a set. And the set of numbers is negative 5/2, comma 1/2. Once again, it's not an interval, it's a solution set. Let's try the next one. Once again, I'm going to resize this just a little bit. Give me a little bit more room to play. Maybe. There we go. All right. And actually, we've seen the instructions. So, don't have to isolate the absolute value. This is ready to go. So we're going to create 2 different equations. Either 3x minus 12 is less than 6 is our first inequality. And our second inequality is 3x minus 12 is greater than negative 6. Remember that when we create the negative version of the inequality, we have to flip the inequality. And so now we're just going to add 12 to both sides, and I'll get 3x is less than 18. Divide both sides by 3, and I'll get x is less than 6. Over here, I'll add 12 to both sides, and I'll get 3x is greater than 6. Divide both sides by 3, and I'll get x is greater than 2. Now, remember, our trick we learned earlier, absolute value less than absolute value is small, which means we're going to end up with that barbell shape. And so if we have the barbell, then this could be written as a compound inequality. We said x is less than 6, that's the part from over here. But we also said x is greater than 2. And our interval is, we start at 2 and we end at 6. But the endpoints are not included. So we use ellipsis, not square brackets. All right, for this one shouldn't take long. Have to isolate the absolute value, subtract 5 from both sides. I get the absolute value of 10x is less than negative 1. Now remember, absolute value always, if we apply the function, we always get a positive answer, and we cannot have a positive number less than a negative answer, so this is no solution. We can either write an empty set, except either of those answers. All right, show last one of these. And this one's different. This is greater than or equal to. So already we know that our graph is going to have this shape. It's going to be an or statement. Save that down here because we know that's coming. So we're going to create our two different inequalities. 2x minus 8 is greater than or equal to 4, or 2x minus 8 is less than or equal to negative 4. And once again, when we create the negative version of our inequality, we have to flip it. Add 8 to both sides. I'll get 2x is greater than or equal to 12. Divide both sides by 2. X is greater than or equal to 6. Over here, I'm going to add 8 to both sides, and I'll get 2x is less than or equal to 4. Divide both sides by 2. I'll get x is less than or equal to 2. So closed circle here. Once again, they're closed circle because this time it is not just less than, but less than or equal to. So it's less than 2, so we go down from 2, and then greater than 6, so we go up from 6. And our interval this time is going to be a little bit more complicated. It's negative infinity up to 2, with 2 included, and 6 to infinity. And it's the union. Remember, that symbol here means union of those two sets. All right, make a table for each function. Be sure to include the vertex, graph each function. All right. Once again, you will be able to use your calculator on this, so by all means, please do. I mean, yes, if you want to really grind it out by hand, that's fine, but let's double check our work on the calculator. So I tell you what, I'll show you both ways. I'll do it by hand, and then I'll show you how much easier it is to use if we have our TI-84s. So I'm going to pick some points. Now, I already know where the vertex is because this is a quadratic function, so we already know it's going to be that U shape, as you guys say, which is a parabola. And it's going to be shifted to the right 3 and up 1. So that's going to be the vertex of the parabola, because this is the shift to the right, and that's a shift up. So I know that point's going to be there. So I'm going to make -3, one of the values on my thing. Now I got to double check this. I'm sorry, +3. Oops. +3, 1 had better be one of the points on my graph. So f of 3 equals 3 minus 3 squared plus 1, which is 0 squared plus 1, which is 1. Sure enough, there's my point. And I can plug in other points as well. I could plug in 1, 2, 3, 4, and 5. When I plug in 2, I will get 2. When I plug in 4, I will get 2. Same thing as before, just plugging them in. When I plug in 1, and I'm not doing all the points because I would hope that you could do the arithmetic. So I plug in 1 and I will get, for example, 1 minus 3 squared plus 1 is -2 squared plus 1, which is 4 plus 1, which is 5. As it turns out, 5 will give me the same value. Sorry, wrong point. And there's my parabola. And I promise to show you how much easier this is to do on the calculator, and so I will. So, I was doing a problem here before, I guess. All right, I don't know what was going on. So, put the function in. Someone has been using your calculator before class. Clear what they were doing out. Remember, actually, there's a lot going on here, so let's just go second plus 7, 1, 2. Oh, seems to be a little bit off. Second plus 7, 1, 2. There we go. Ram's clear. Starting with a fresh calculator. So the equation was y equals, and just type it exactly like we see it, x minus 3 plus 1. And if we look at the graph, oh look, our graphs look the same. But the key for this is to then go to the table of values. And there we can see our values. 1, 5, 2, 2, 2, 3, 1, 4, 2, 5, 5, which are exactly the values I got. And so if you use the calculator and you use the part of the graph that says table, then you can have the calculator construct the table for you. We'll come back to that on the next problem. So domain, well, this function is going up, but it's leaning out ever so slightly. So it's going to go this way forever, and it's going to go that way forever. So the domain is going to be all real numbers. -infinity to infinity. The range is the functions going up, and it's starting at 1 and going up forever. So the range is 1 to infinity. And remember, when you do the domain and range, stay on either the x-axis or the y-axis to see where the function projects. All right, so this one, make sure to use a table. Show where the vertex is going to be. This is an absolute value, so I know I'm going to get the V shape. But it's negative out front, which means that instead of opening up, it's going to open down. And +3 means it's going to be shifted up 3, which means that this point is going to be on it. So 0, 3 is going to be one of my points. And so what I want to do now is let's just go ahead and have the calculator give me the rest. Let's make my life easier. So go back to y equals, clear what was there, Now, a lot of us forget how to do absolute values. So remember, the easiest way is to do alpha F2. And there are my absolute value bars. Now the negative was in front. And remember, when it's a negative like that, whoops, I erased it. It's not the minus symbol. You actually have to use the negative button that's down here on the bottom. Now we have to arrow outside the absolute value, plus 3. Now our graph looks a little fat, but remember, the tip was whenever we want it to look exactly like it would on graph paper, we use zoom standard, which is 6, and then we follow that up with zoom 5, and that makes sure it's not stretched and it looks exactly like it would on graph paper, which is that. And then we can get our table of values here, and we can transcribe them. So it's 1, 2, 2, 2, 0, 3, and so we can plot those points. Wait, I mistranscribed those. It was 1, 2, and 2, 1, which are there and there, and then negative 1, 2, and negative 2, 1. And we can see since the arms of the absolute value are straight, once we get a few of the points, we can just continue that pattern on, and there's our absolute value. So the domain, once again, no restrictions on the domain. The two arrows go forever in both directions on the x, so the domain is negative infinity to infinity. Or you can think about the individual function. Is there any number that we're not allowed to put in the absolute value function? The answer is no. The range is the function, and a lot of us say the function starting here and going down. But remember, we always describe range from least to greatest. So the better analogy is the function's going up and stopping there. So the range is negative infinity up to and including 3. And because 3 is included, we use the square brackets. All right, circle the letters of a function with the same range as the absolute value, of the absolute value of x minus 2. So if I were to graph that function, it's going to be an absolute value function that looks like this down at negative 2. So I need functions that start at negative 2 and then go up forever. So we'll take this, put that over there. So let's talk about each one of these functions individually. So function A is going to be a parabola that's shifted to the left 3 and down 2. But once again, it's going to start at negative 2. So the range is from negative 2 up, just like it was in our original function. And you can see this by looking at the graph on your calculator. So A will be correct. But this is a technology-enhanced question. This is the kind of question on the SOL where we'd click on it and they would highlight yellow. So there might be more than one right answer, so we got to be careful. So let's try B. Once again, we're looking for things that go from negative 2 to infinity. And if we were to graph this one, we would see that it would start at 2 and we'd have a parabola up. So the range on this one is 2 to infinity. And we're looking for graphs that are the same as the original, which was negative. Sorry, I can't write up there on the smartboard. We're negative 2 to infinity. Ooh, smartboard's way off. I'll write it over here. Close enough. So we're looking for things that have the same range as that. It's too big. So this one does not have the same range, so it's out. C, if we were to look at it, would look like this. And this point here would be -4, but it's going to go down just a little bit further. This function actually has a horizontal asymptote at y equals 5. And so the range on this function is 5 to infinity. And because it's an asymptote, it never touches. It just gets really close to 5. But once again, that is not the same range, so that one's out. For D, if we were to look at it, it's going to be a square root function. And it's going to start right here at -2 and go up, which is what we're looking for. So D does have the same range. The last one is the tricky one that causes us a lot of trouble. Causes a lot of our trouble. Sorry, excuse me, with domain and range, which is that this function, if we look at it, is going to be over here at 2 on the x-axis, but it's still starting at 0 on the y. So the range is 0 up, which is not the same as the original function we're looking for, so that one's out. So on this one, if this had been on the SOL, you would have been expected to highlight A and D. And I think we're on to our last problem. And we're going to have to break back out the calculator. The concentration of a medication in a patient's blood as time passes is given by the following data. So does the data appear to be linear, quadratic, or exponential? So we're going to have to put the data into our calculator. So how do we do that? Now, we were doing another problem before, so maybe I'll just reset the whole thing. Well, maybe not. Second plus 7, 1.
All members of the girls' varsity cheerleading squad, please report to the principal's conference room. All members of the varsity cheerleading squad, please report to the principal's conference room. Thank you.
Okay, so stat, edit, and we're going to put the data in. So we'll put the time into X. I obviously checked the data every half hour. Very important that we make sure we enter in our data correctly. Now, the data is in the calculator. But if we want the calculator to display it, we need to ask it to. So we would go up to stat plot, and we would make sure that the plot is on, and that right here we have the scatter plot selected. So then we want to show the data. So we need to zoom to our stats data. which is zoom 9. And there, once again, so the question is, does the data appear to be linear, quadratic, or exponential? Now that clearly is a parabola. Now I'm just going to draw it on with my own pen. It's not a perfect parabola, but it's pretty close. And so it's definitely, given the three choices of linear or exponential, the only one that makes any sense at all is quadratic. Then we need to find our line of best fit, or in this case, curve of best fit. So we're going to go back to stat, and we're going to calculate. And since we said it was a quadratic, we are going to use the quadratic regression. We said our x's were L1, perfect. We said our y's were L2, good. We're not doing any frequency lists. And so then we're going to have it write the formula when it calculates it, or write the equation when it calculates it into y1. So we'll come down here to calculate, and there is our equation. So we said this was a quadratic. And it was negative 56.21. Remembering. Plus 139.31x plus 9.35. And we said x represents time. And we said y represents concentration in milligrams per liter. So based on your model, how much medication would be in your patient's blood after 3.5 hours? So all we're going to do is we would plug 3.5 in for x. So it'd be y equals negative 56.21 times 3.5 squared plus 139.31 times 3.5 plus 9.35. Now, oh, whoops, that's not what I wanted. I wanted the table. So one of the tricks you can do, well, maybe, if you can get the thing to recognize my key punches, is when you go to table setup, this was how the table works. And you're telling it what value you want to start at, and you can also tell it how much to change each time. So now, when I go to my table of values, starting at 0, and this is not our actual values, this is what our prediction equation is predicting from medicine concentrations at these different times. And as you can see, at 3.5, it's giving me the value that I would get if I had calculated this out, which is y equals negative 191.7 milligrams per liter. But this is where we have to ask ourselves, can we have negative values of medicine in our blood? And the answer is no. We have to look at whether the model makes sense. Certain models, it does make sense to have negative values. In this one, it does not. Instead, what would happen is your medicine goes in your body and comes out, and then when it hits 0 again, it would stay 0. It would not go negative. So we would say the answer, how much medicine would be in the patient's blood after 3.5 hours? 0 milligrams per liter. And that is it for the review. Good luck on the quarter exam. Be prepared with questions when you come to class.